So thank you very much for being here, especially after the dinner and so early. So I'm going to present the work that we have been doing for a couple of years now with my master student, Carlos Rubio. The original idea was to bring him and to come and present the main results of his work. But the guy went too fast, so he got hired very quickly. And now we want a partner for in the industry sector. So probably I missed a PhD student, but I prefer to see it like I want a industrial partner. Okay, so this is the agenda. I will talk a little bit about the motivation of this work, the problem statement, the numerical formulation and results, including wave patterns, wave instabilities, and force coefficients on the oscillating foil, and conclusions and present and future work. Okay, so the motivation for this work is that at the Escuela Nacional de Estudios Superiores, Unidad Mérida, we are located in South Mexico, in Yucatan Peninsula. So we have a very, very strong group of physical oceanographers who have been doing great efforts to assess on the availability of renewable resources based on marine currents. So typically what the guys would do is to make measurements all over this point, and we can get a lot of information with the instruments of these groups. So the outcome of this research is that there are a lot of currents that are not so intense in the Yucatan Peninsula. So the typical devices to harvest energy there will be, well, not very beneficial. So we want to design and to develop some, let's say, current-oriented devices for let's say low-speed currents. Okay, so the guys were there, and I arrived from the Barcelona Supercomputing Center. By that time, I had already been working with fluid structure interaction problems. So in this case, this is the case that I studied the most. And so it was quite natural to go and reinforce the team and to see if we can provide some insights and probably help the engineers to construct some machines that they were wanting to design and to build. Okay, so in that context, we came with this very simple proposal. This is an airfoil constructed with just a circular sector and two planes, and this was chosen mainly because they were already working on this. So it's a good idea to work with something that is already in progress. So the boundary conditions are indicated here. Far upstream, we have a uniform profile. We have periodic boundary conditions in the sidewalls. The other surfaces are no-slip surfaces, and for the outlet, we have a zero stress outlet. Okay, so we want the foil to oscillate with a prescribed motion. The idea would be to check the lift that we can get, the drag that we can get, and based on that, try to design a machine plunging or probably a vertical turbine. Okay, so this area highlighted here is the one we use to non-dimensional the hydrodynamic forces, and the angle that we get here is just to get this A parameter, that is just the amplitude of the oscillation, to 2. So the angle is 0.28 radians. We have different aspect ratios, different core lengths, but for these results, we chose just one. The chord is 4. Well, this is the quantities that you can see. Okay, so what we use the Navier-Stokes equations in the ALE formulation. The ALE is needed because we are going to move the mesh. So this only introduces this domain velocity in the convection term. And we have these two relevant parameters. We have Reynolds number and Strouhal number. The Strouhal number is just a non-dimensionalized frequency. So we have the frequency of oscillation, and we select the diameter of the foil, of the front size of the foil, and the far upstream velocity. Okay. So how did we solve this? We used the ALIA code. I was working with ALIA for a long period, so it was quite natural to train Carlos to use it. So it was quite easy because for the time being there are a lot of tools and documents and a lot of work done. So it was really easy to get Carlos into the code. I think most of you already know it, but it's a stabilized finite element discretization. I used a temporal scheme as a second order PDF, and the simulations were done at Node 3, but at that time, I think it's Node 4 now. But anyway, at BSC, Hypatia, it's a small cluster that we have at NS Merida. It was also a very important thing to do to bring the experience that I gained at the supercomputing center. So we built just a very small cluster, 6 nodes, but it's perfect just for training of young people. We have undergraduate programs, and they are already sending jobs and doing stuff. And the cluster of the National University of Mexico, that is called MISLI. Okay, so the parameters that we have, given that the velocity of the currents are not really high, and that we are aiming first to design a experimental device, it's going to be experimental, but the experiment will be carried out in a coral reef lagoon or in a natural site, but with a low speed current. So the Reynolds number is more or less this. And the Strouhal number, we have covered this parameter space, and we are still running a lot. So we have to cover this with more detail, but that's an ongoing work. So we have the FSI simulation used in ALIA that we have used for many studies before. We have the meshes built with the ANSA preprocessor. In case you don't know it, it's an extremely friendly for the user preprocessor. You have a very good support team, and we got 3D meshes with this sizes of elements. We run between 64 and 256 MPI parallel process, depending on the Reynolds number. Okay. So first, what we get is the different wakes that you can get according to the Strouhal number. If the foil is oscillating too slow, so vortex shedding can occur, let's say 2 times. If you see here, you have four vortex shed per oscillation cycle. Okay. If you increase a little bit the Strouhal number, so it gets just 1, but you can get inline vortex Kalman street. Let's say the normal vortex Kalman street with a little bit higher frequency, and the reverse vortex Kalman street with an even higher Strouhal number. This specific wave pattern can provide thrust for the foil. So it's quite interesting to play with these patterns and probably try to change between them, depending on the part of the cycle of the machine that is going to be built. So that's part of the study that is being carried out now. So for a constant Strouhal number, if you increase the Reynolds number, well, you can have, for example, in this case for Reynolds 500, you have 2 triads of vortex per oscillation cycle. Okay, so this has a 3D structure at some point. For example, in this case, with the same Strouhal number, but different Reynolds number, we started seeing these undulations in the wave patterns. And this was associated to flow instability. So we divided this in zones and took some averages between the vertical structures here. And we thought of this as if it was the classical Taylor-Couette instability, mainly because if you see the undulations, it reminds very much that case. In the classical case, you have two solid cylinders that are rotating about the common axis. In this case, we don't have solid structures, but if we subtract the average flow outside the wake, then we can get a flow that are more or less cylinders, and we can apply the Rayleigh criterion. So with this criterion, the lower the values, the more unstable of the flow. So it doesn't fulfill, it never gets to 1, but it gives a clear idea, and these points with low values correspond very well to those with flow instability. So we have a way to measure this. Okay, so the main output of this work for the experimental group are these curves that are the force in the x direction against the force in the y direction. So if you see here for a constant Reynolds number and varying Strouhal number, you can have very, very large differences in lift and in drag. But it is just based on the speed of the oscillation, because the amplitude is just the same. And for constant Strouhal numbers, you can have very, very different behaviors in the drag. Well, it's difficult to call it drag because it is not in the line of the foil, right? It's in the x direction. So the force in the x direction get this shift, and we feel that we can take advantage of this also here. If you see the larger Strouhal numbers, can give you at least no drag. You can stay there and you don't have to pay the flapping does the work. Okay, so I believe it's quite it. So what can be said, the conclusions and the future work is that we have a flow characteristic and hydrodynamic forces for this case. Okay. The experimental designs for energy harvesting devices are in progress. We want to build something and we want to put it in the sea. So it's a major challenge, but we have colleagues in the Engineering Institute that are working hard for this. Okay, so the exploration of the parameter space for this configuration continues. These are partial results. And also we are considering nonlinear oscillation options instead of just a sine. Why is that? Well, because if you want to get a optimal or close to optimal angle quickly, let's say if you have a plunging device. So when it comes down, you want to get it back as quickly as possible. So we do like, let's say a van der Pol oscillation with a fire and charge behavior. And we are now doing these simulations, but that's ongoing work. Probably future part CFDs, we can show some results. Okay.